Hi folks, how are you? I hope you are well and that you had a good morning. If you can hear me, please thumbs up in the announcement I just made into the Q&A. Okay, I see you can hear me. Thank you very much. So today we are going to continue with the part of this module related to arithmetic for computers. Remember that, as always, the part of the content in these slides is based on the book using this part of the module. So basically today what we are going to see is the IEEE 754 floating point standard. As far as I know, you have already seen this in the network part with Charles, but I'm interested in reviewing it in the context of the architecture part also, because later we will need this in order to explain the next parts of the model. Okay, so this is just a review of this standard. Okay, so let's start then. I think you have already seen this, maybe using another format, but basically the idea is the same. So with this standard, the IEEE 754, we have two options, the single precision and the double precision, and it's used to represent floating real numbers in binary. So what we have here is how the bits are allocated using this standard. For instance, here we have the S, which is the sign. So the bit placed in this position, in the leftmost position, is the sign. A 0 here means it's a non-negative value, and a 1 here means that is a positive value. Okay, the next part is what we call the fraction. The fraction is actually what we also call the significant subtracting 1. So you could imagine that if we normalize the fraction, which means that we have the fraction between numbers 1 and 2. So this is what we call the significant. This is going to have always a leading one. Okay, in this case, imagine that the significant, the real number we want to represent, is 1.0. So we are going always to have a 1 here. So what we are doing here is, okay, if I know that I'm going to have always the number 1 here, I can remove it and just save that space for decimals. And this is what we are doing. In the fraction, we are storing the significant, but without the leading one. So the significant, as we mentioned here, will be the fraction plus the 1 point restored. And then we also have the exponent here. So for the exponent, we actually are not putting here the real exponent. We have what we call a bias exponent. This is to ensure that the exponent is unsigned. In the case of single precision, the bias is 127. In the case of the double precision, the bias is 1023. And for getting this representation, we just add this bias to the actual exponent. So then, more graphically, with single precision, we have 32 bits for representing a floating point number. In this case, the sign will be in the left part, as we have seen. Then we have 8 bits for the exponent and 23 bits for the fraction. Similarly, for the double precision, what we do is extending the number of bytes devoted to the exponent. So here for double precision, we have 11 bytes. And for the fraction, we have in total 53 bits. Okay. So let's see a simple example. For instance, let's say I want to represent this number in single precision. Okay, so first of all, I will check for the sign bit. So in this case, the sign bit is positive. So we will add 0. Okay, and we will add 0 in this position. Make sense? Then the next part is the fraction. In this case, it's very easy because the fraction is just 0. Remember that we need to remove the leading one. Okay, so the significant is the leading one plus the fraction. As we know that when the number is normalized, this bit here is going to be always 1. We can remove it and add it afterwards. So here, what we need to store actually for the fraction is 0. And in this case, it's very simple. It's just everything zeros. And then the exponent. So in this case, the exponent is -1. If I add the bias, in this case for single precision, the bias, as I have mentioned, is 127. So with this, we have this number in binary, which actually is the one I place here. And with that, I will have the single precision representation in IEEE 754 floating point standard of this number here. Okay, so similarly for double precision, it's the same, everything is the same. The only difference here is that we have more bits for the fraction. So here we can use 52 bits for the fraction. Okay, and then everything will be exactly the same. Make sense? Okay. So now I have an exercise for you. So as I think that you have already seen this with in the network part, I would like that you tell me how what number is represented by this single precision float. I'm going to give you some time to do this. Okay, I'm going to give you 4 minutes to do this. I'm going to also put a link to a form in the Q&A, and yeah, and we will check the result later. Okay, so good luck. Okay, so the time has finished. Let's check the results. I don't see any response. Okay, now I see some responses. So this is what I see. So most of you think that the result is -5. So let's check if that is the correct answer. So first of all, I have just put colors here. So for the sign, it's very easy. So it's 1, so it will be a negative number. Then for the fraction, we have here in gray color. This is the fraction. Some people is asking if fraction is the equivalent to mantissa. Yes, mantissa fraction are similar terms for the same concept. Then what we need to do is for the fraction, okay, if we have this fraction or in binary, what is the equivalent number in decimal? So I'm going to show you a possible way of doing that. There are other ways. In this case, what I'm doing is I have the first bit of the fraction and I multiply by 2 power -1. Then I have the second bit of the fraction and I multiply it by 2 power -2. And then I will do, if I will have more bits here other than 0, I will do again that, but here I don't have any one, so this will turn out to be all of them 0, but if I have ones here, I will do the same. Okay, so in this case, I only have those two positions. This one is going to be 0, this one is going to be 1. I'm just doing all this just for completeness. Okay, so after doing all these operations, we got that this number is decimal, this number in binary is equivalent to this number in decimal, okay, 0.25. Okay, then, so now we have the fraction, we have the sign, we have the fraction, and now the exponent. So for the exponent that we have here in gray color, sorry, the exponent we have here in green color, okay, we just convert this to decimal, and then remember that it's a bias exponent. So we need to subtract from this exponent the bias in order to have the actual exponent. So with this, we have the sign, we have the fraction, and we add 1, remember, for having the complete significance to restore it. And then we have the exponent. And with this, if we do the calculations, we have, some of you has guessed, we have -5. Okay? So I think this is clear. Let's do another example just to check, now that you have refreshed your mind, just to check if you can do this. So let's do now the same, but in this case, I want the number in double precision. So this number here is in double precision, and I would like to know the number in decimal. Okay, so again, I give you some time. I will also put a link in the Q&A, and yes, good luck. Okay, the time is over now. So let's see the results for this. So in this case, most of you say that the result is minus 0.75. Let's see if that's correct. So first of all, as before, the sign in this case is a negative number because we have a 1 in this position. Then the fraction, which are those bits here in gray. So we have this value in binary, and again we want to know the equivalent for those values in decimal. So similarly as before, what we are going to do is we multiply the first bit by 2 power minus 1, the second bit by 2 power minus 2, and in this case again all the rest of the bits are 0. If I had more bits, I will just multiply them, but in this case, as are zeros, I have just not put them here in the slide for the sake of clearness. So here, in this case, we only have this value actually having a 1, the rest is 0. So we get that this number here following these calculations is 0.5. Okay, I think that this is clear. If not, just let me know, please. So then we have the fraction also converted to decimal. And then what we need is the exponent, the green part. So in this case, for the exponent, what we have here is this number in binary that converted in to decimal is this one. Remember that the exponent is bias, so we need to subtract the bias, which is precisely what we are doing here. Okay, so we have the sign, the fraction, we add 1 because we need to restore this one, the leading one, and then we have the exponent from which we subtract the bias. And if we do all those calculations, in the end we get minus 0.75, which is the answer that most of you has tell in the form. Okay, so I think it's clear. Okay then. So then now let's do the other way. Now let's assume that we have this decimal number minus 0.7 and that we want to convert this to single precision. Okay, so I'm going to give you again some time to do this, and I will also put a link to a form in the Q&A. Okay. Okay, the time is over. So let's check the results. Okay, so most of you answered the correct question, the correct answer. So let's see. How we convert this decimal number into single precision IEEE 754 floating point standard. So the first step will be converting this decimal number into binary. So I'm going to show here just a method to convert it. There are other methods. You can use the one you prefer. So here, for instance, what I'm doing is I just multiply the decimal number by 2, and if the result has a 1 before the point, I just add here a 1, and if it is a 0, I will put here a 0. Okay, so first of all, I multiply this by 2 and I get this value, and as there is a 1 here, I put a 1. Okay, I then multiply again the resulting value minus the 1. Okay, so this 0.4 comes from here, subtracting the 1 that we have put here. Okay, so we have 0.4 by 2, which is 0.8. In this case, we have a 0 in the before the point, so we add here a 0. Okay, and then multiply again. 0.8 by 2, in this case, is 1.6. So we have a 1 here, which is actually the value 1 that I put here. And then the remainder is 0.6, which is the one I multiply by 2. And I get 1.2, which gives me a 1. And then the remainder is 0.2, which I multiply then by 2, which gives me 0.4. I have a 0 here, and I put the 0 here. And now, if you see, this 0.4 is a value that we also have had here. So this means that this is going to be repeated like in a loop. So from here, if I multiply it by 2 again, I will get the same values again, and this will run in an infinite loop. Okay, so this will be repeated. Make sense? So once I have done this, I have here 0.7 in binary. So this will be the most significant bit, and this will be the least significant bit. So then we have that 0.7 in decimal is equivalent to 0. And this number in binary. So if you notice, so we have 1 0 1 1 0 1 0 1 1 0, but we have mentioned that this is a loop. So those 4 bits are going to be repeated again and again. So this is what we have done here. Okay, and then depending on the precision we have here, depending on the bits we can represent, we have available, we will have more precision or less precision. Make sense? So the step 2, once we have this number in decimal converted to binary, is normalize, use the normalized scientific notation. What this means? This means that we want a 1 here in the before the point. Why we want a 1 here? Because remember that in order to represent the fraction, we were assuming that we always had a 1 here. So what we do is, if we have this number and if we want have this one move this one to the left, we need to multiply this by something. So in this case, the initial number will be equivalent to multiplying this by 2 power 0. 2 power 0 is 1, so anything by 1 is 1. But if I want to move this 1 after the point, before the point, so move this one, shift it to the left, I will just multiply it by 2 power minus 1. Okay, and by doing this one here shifts to the left. And with this, we have, in this case, the value normalized, because we have here a 1, okay? A 1 before the point. So now that we have this number normalized in scientific notation, we can represent it in single precision, okay? So in this case, what we are doing is the easy part, which is the sign. The sign is 1, negative, okay? So we have a negative sign. So then we have 1 in the sign, and we put a 1 here, okay? Make sense? Are you following me? Then the fraction. Remember the fraction, okay? The fraction is the value without the leading one, without the 1 point, without the 1 point. So we only put the decimal part, okay? So starting 0, 1, 1, this is the only thing we are going to put in the fraction, because we assume that there is 1 before the point. So then we will put this value, which is the fraction, which is this one. We will just put it here. And now here you are able to understand the difference between single precision and double precision. So remember that here we have mentioned that to represent this number, there were a group of 4 bits, 1, 1, 0, 0, which repeats infinitely. So here I have 23 bits. So I can indicate all these bits, but in the double precision, I will have more than 23 bits. I think it's 52 bits. So I will be able to add more bits here. Therefore, I will have more precision to represent the decimal number. Okay? And then finally, the exponent. So in this case, the exponent is -1, the real exponent. But remember that we need to bias it. So -1 plus the bias, that in this case for single precision is 127. As we have mentioned, we have that the number for the exponent will be 126. That in binary is this value, and is actually what we put here, okay? So by doing this, we have the number in single precision. Make sense? Okay then, so now I want you to do the same, but for this number, for 13.3, okay? I'm going to give you again some time to do this, and I'm going to place also a link to a form, okay? Good luck. Okay, the time is over. So I hope you had time to finish this. Let's see your answer here. Yeah, most of you have the correct answer. Let's check this. Some slides. Okay, so first of all, the step one, we are going to convert, first of all, in this case, we have some digits before the point and some digits after the point. So first of all, we are going to convert the digits before the point. In this case, the number was 13.3, so we are going to convert first the 13, which was in decimal, to binary. So I'm going to show you a method here. You can use any other method. This is just the method I use. So in this case, for converting the decimal number before the point, remember that in the example before we were converting the number after the point and we were multiplying by 2. In this case, we are converting the number before the point and we are dividing by 2 instead of multiplying. Okay? So we are going to convert the 13 first. If we were going to convert the 0.3, the decimal part, we will be multiplying by 2. In this case, for the part before the point, we are going to divide by 2. Okay, so similarly then to before, I have 13, I divide it by 2 and I get 6 and the remainder is 1. And I continue. I have 6, which is this 6 here, 6 divided by 2, the result is 3 and remainder is 0. Then 3, this 3 here, divided by 2 and the result is 1 and remainder is 1. Okay, are you following me? Then this one here comes here and I divide it by 2. The result is 0 and the remainder is 1. And as the result is 0 here, this means we have finished. And in this case, we need to read this number from bottom to top. So here is the most significant bit at the bottom, and at the top is the less significant bit. So this means that 13 in decimal is 1101 in binary. Okay, there are other ways of converting from decimal to binary. I just wanted to show you this way. Okay, then we are going to convert the decimal part, the 0.3, the part after the point, and similarly to what we have done previously, we are going to multiply this number by 2. Okay, so in this case, 0.3 multiplied by 2, we got 0.6. We have the 0 and we put the 0 here, and then the 0.6 we move it here, so 0.6 multiplied by 2 is 1.2. We conserve the 1 and the 0.2 we pass it to the next iteration and we do 0.2 multiplied by 2, it's equal to 0.4. I have the 0 here, I put the 4 in the next iteration, I multiply again by 2, this gives me 0.8. Again, we have a 0 before the point, which is the value I conserve. Then the 8 goes to the next iteration, I multiply it by 2, I get 1.6. I conserve the 1, and for the 6 I check and I see that, wow, this 6 is the same I have here, so it happens the same as before. I have a loop, so this will be repeated again and again and again. Okay, are you following me? Remember that in this case, the order in which we read those values is from bottom to top. So here we will have the most significant bit at the top, and at the bottom we will have the less significant bit. So this means that 0.3 in decimal is equivalent to this number in binary. Okay, so 0, 0, 1, 1, and 0, 0, 1, and then remember that this is going to be repeated again and again. So those 4 bits are repeated again and again. And similarly to before, we will have the amount of these bits depending on the bits we have available for representing this number. Okay, I think it's clear. If it is not clear, please let me know. So now we are going to normalize this number inside different notation. So initially we have put here the 13 that we have converted previously in binary, and here the 0.3 that we have converted in the previous slide. Okay, so this is the initial value we have in binary. Remember that normalize means that we only want a 1 before the point, so we need to shift this 1, 2, 3 positions. So the initial number, remember, is equivalent to multiply it by 2 power 0. As I have mentioned, 2 power 0 is equal 1. So anything multiplied by 1 is the initial value. Okay, if I want to shift this 1, 2, 3 positions, what I need to do is multiply it by 2 power 3. Okay, every position I move is I increment 1 the power of 2. Every position I move to the left, if I'm moving to the right, then the power will be negative, as we have seen before. Okay, so here I have moved 3 positions to the left. I multiply it by 2 power 3, and I have the number normalized. Great, so we have the number normalized. So now we are going to represent this in IEEE 754 floating point standard, single precision. So the easy part, the sign is not negative, it's positive. So the sign will be a 0, and this is what I put in the sign bit. Okay, this is easy. The fraction, remember that we are going to ignore the leading one. We are only going to represent everything after the point, because we assume that this leading one is implicit. Okay, so then we will put these bits from the fraction here, and again in this case we have only 23 bits because we are in single precision. If we were in double precision, we will have 52 bits, and we will be adding more bits. And finally the exponent. So in this case we have 3. This is the real exponent, but we need to add the bias that in single precision is 127. So 3 plus 27 is 130. That converted to binary is this value, and is actually what we are having here. Okay, makes sense? Okay, so this is what I have for you today, reviewing this floating point standard. In the next lecture, we will see addition and multiplication, but not with integers, with floating point. And now I'm going to check if there is any question I can address before we finish the lecture. Let me check. So someone is asking why I was multiplying by 2 in the first converting from floating point example, and now I am dividing by 2. So as I have mentioned, I have shown you a method for converting from decimal to binary. Okay, so if I want to convert from a number, from a decimal number, if I want to convert the integer part, which means the part before the point, in this case the 13, I need to divide by 2. But if I want to convert the part after the point, the decimal part, I need to multiply by 2. Okay, so for the integer part, I divide by 2. For the decimal part, I multiply by 2. And this is what I have actually done here. For the decimal part, I have divided by 2. This is the 13. The number before the point, And for doing the same for the number after the point, for the decimal part, in this case 0.3, I'm going to multiply by 2, okay? Before the point, for converting before the point, divide by 2. For converting the number after the point, multiply by 2. Let's check if we have. Okay, someone is asking, how do we know when we need to add the number to the bias and when to take it away? So here, for instance, if I'm converting from, if I have the actual exponent and I want to represent this number in the IEEE 754, then this is the actual exponent, the real one. So then I need to add the bias, and need to add the bias and put it the resulting number here. If I was doing the inverse, so if I have the floating point representation in using this standard, what I will need to do is the inverse. So if I have this number here, I will convert this number to decimal, which is 130, and I will subtract the bias, which is 127, and I will get the 3, which is the real exponent. So it depends in what I'm doing. If I'm converting a real exponent to the single precision format, I need to add the bias, and if not, I need to remove it. Okay. Okay, thank you very much for listening. You have additional questions, you know, we have the ticketing system available, and I'm also happy to help always. So have a nice rest of the day. See you tomorrow morning. And yes, thank you very much for listening, and I hope you have enjoyed the lecture. Thank you so much. Bye bye. See you.